This resource is the fourth in a 5-part series on the normal distribution. Part 1 looks at the basics of the normal distribution. We discuss the distribution about the mean and the probability of an amount lying between integral multiples of the standard deviation. Part 2 considers the process of normalizing a value. Part 3 considers the probability a normally distributed value will lie in some range. Part 4 combines the ideas presented in Parts 2 and 3, finding percentages for examples that require normalizing the value first. Part 5 looks at how to find the variable value that define various percentile ranks in a population, which means a specified percentage of the population is less than that value for the variable. In a previous resource, we saw evidence that 10-week-old kittens have an average weight of 25 ounces with a standard deviation of 4 ounces. Suppose we are about to adopt a new kitten. What is the probability that the randomly selected kitten weighs less than 12 ounces, or more than 30 ounces, or weighs between 14 and 32 ounces? To find the probability that our kitten weighs less than 12 ounces, we have to normalize the value with the mean and standard deviation of the population. The probability that the weight is less than 12 ounces is equal to the probability that the z-score is less than the quantity 12 minus 25 divided by 4. We want to find the probability that the z-score is less than negative 3.25, or that we are more than 3.25 standard deviations below the mean. Looking this up in a cumulative frequency chart, we find that the probability is 0.0006, or 0.06% likely. But what if we want the probability that the kitten weighs more than 30 ounces? We need to find the probability that the z-score is greater than the quantity 30 minus 25 divided by 4, which is the same as 1 minus the probability that z is less than the normalized value. The probability is equal to 1 minus the probability that z is less than 1.25, which means we have 1 minus 0.8944. This equals 0.1056. We can also find the probability that our kitten weighs in the range from 14 through 32 ounces. We need to find the probability that z is between the normalized values for each, which is the probability that z is between negative 2.75 and positive 1.75. To find this probability, we subtract the p-value for the upper bound minus the p-value for the lower bound. We have the probability that z is less than 1.75 minus the probability that z is less than negative 2.75. We look up those values in our handy cumulative frequency chart, subtract, and find that there is a 95.69% chance our kitten weighs between 14 and 32 ounces. Let's see some more examples. We saw earlier that for women aged 20 through 29, the average height was 69.1 inches, with a standard deviation of 2.75 inches. What is the probability that a randomly selected 20-something woman is less than 73 inches tall, more than 58 inches tall, or between 60 and 72 inches tall? To find the probability that a woman is less than 73 inches tall, we need to normalize the height by subtracting the mean and dividing by the standard deviation. The probability that the height is less than 73 is the same as the probability that z is less than 3.24, which is 0.9994. The probability that the height is more than 58 inches is the same as 1 minus the probability that z is less than 58 inches normalized amount. We want to subtract 1 minus the p-value for negative 2.22. We have 1 minus 0.0132, or 0.9868. To find the probability that a randomly selected 20-something woman is between 5 feet and 6 feet tall, we find the probability that z lies between the normalized values for each. So what we really need to find is the probability that a z-score is between negative 1.49 and 2.87. So we will subtract the p-values for negative 1.49 from the p-value for 2.87. Looking up the values, we have 0.9979 minus 0.0681, or 0.9298. Another way to think about this information is that 92.98% of women in their 20s are between 5 feet and 6 feet tall. Remember discussing Margot Dydek, the women's basketball player that was 7'2"? Doing the calculations for a z-score of 7.9, we find that there is only a 0.1309% chance that a woman would be as tall or taller than Margot.